Good morning, everyone. Hi. How many malware analysts here in the crowd? People who analyze malware. Few of them, not many, not many. Okay. I've seen a lot of talk about dealing with malware, malicious code, and stuff. What I want to talk about is how can we use a malware to catch a malware. I needed a catchy topic title, so that's a catchy title there. All right. So, little introduction on myself. My name is Arun. Uh, I'm a professor at University of Louisiana at Lafayette, and I also have a startup, Cytherial. We did some research for DARPA some time back, and we've converted that into a service, a product. And my strength, or at least my expertise, is in automated malware analysis and indexing. So it's not just analyzing malware, but also indexing, so you can search and it can do more from malware, and also automatically extracting rules to detect malware. First, a little public service announcement. How many of you write blogs? No? No? So we had some very good talks here, great presentations. And I'm an academic, but I spent a lot of time in Black Hat and Virus Bulletin and a lot of the commercials or practitioners conferences. And what I find is there's a good amount of knowledge that is presented, but it's not archived. Archived as in academics speak about archive as in something that you can leave and can be found 20, 30, 50 years from now. So your blogs, yes, they are good. They can be found in the next year, 5 years maybe, but over time they're going to be history. But you may have a lot of good knowledge, nothing left behind. What we've created is a journal, ACM Digital Threats Research and Practice. I don't know if Lee is here. So I'm a co-editor of this journal with Lee, and we have a specific type of paper called field notes, and that's aimed at practitioners. All right, so it's not where you got to say, hey, this is this research, and you don't have to put it in context of related works and all of that story that you typically have to do for academic research. All you have to say is, here's what I did, here's why it's interesting, here's the data, here's what I think we can conclude. And your conclusion doesn't have to be generalizable. It just has to be one instance that should be interesting, that should be worth for people to know about, and it'll go through some minimal review just to say, hey, yes, this is something of value to the community, and that you've given enough data so people can understand, and so on. So field notes. Please consider submitting your findings to field notes. Yeah. Okay. I don't have a speaking problem. I have a hearing problem. Sorry, I'm not able to hear well. So if you can either speak louder or someone can, I'll take care of it.
Can you submit anonymously?
Can you submit what?
Can you submit anonymously?
Yes. Well, good question. Okay. So I'm speaking off the cuff now. As a co-EIC, I can make some decisions, I guess. Yes, you can submit anonymously. We got to find a way to do it. So the anonymous as in anonymous to whom? There's no one in the EIC, no one knows about it, or when it's published, no one knows about it. So we got to figure out what anonymity means. We don't have absolute zero anonymity at this point, as in you just submit and no one knows who's submitting it. Okay, but if it's a matter of anonymity in publishing, we could definitely attend to that. Okay. So with that, let me digress a little bit. I know this is operational track, and I said we have a little bit of time, so I'm going to digress into a philosophy track here. All right. So here's the question. In this scenario, someone is banging at the door. Will you wait until the door breaks? Most likely you won't. I mean, it's like someone banging the door. You take some action. The door is not yet broken. You're all safe still, but you know someone is banging at the door. You got to take action, right? Now, why do we treat security as a Boolean state? Either it's secure or it's broken, nothing in between. That's not the case with the door. The door is getting weaker. There is a sort of indication that something is going on. And question is, should we not assess if the security is weakening? So we know we are constantly under attack. So that's a given. If it's under attack, can we not also assess, hey, are we getting weaker or the attacker getting stronger on our door, as in your individual door, not someone else's door, not your neighbor's door, not your some faraway person's door. So that's a question. And so you see, how do we assess security state? What does it mean to assess a security state? So typically what we see is when we talk about attacker and defender, we have this notion of asymmetry, that the attacker just need to be successful once, but the defender's got to be successful 100 times. You got to always, right? That's a asymmetry. There is a little corollary to that, is that the attacker must try and fail 99 times before the attacker succeeds. It's like breaking the door. You don't just push the door and it breaks. You got to be banging at the door. You got to be hitting hard at the door, and the door at some point gives way. And it's not the last hit that broke the door. It's the whole bunch of hits that have happened before that are breaking the door. And so here, what I believe we are leaving on the table is the 99 hits that we have guarded against. So can we utilize the attacker's failures? Clearly, an attacker is failing. Can we utilize the attacker's failures to learn? And if we can learn who's the attacker, what's the objective, who's the target, we can learn a whole bunch of things maybe before the door gives away, and maybe put something else against the door to make it a little bit more stronger. Okay? So that's the philosophy track. And so in this case, from malware, what could we do? There's a little architecture sort of thing. If you have a quarantine malware, this antivirus is our gate. Malware is hitting at the gate and antivirus keeping it out. At some point the gate breaks and it goes through. That's roughly what happens. So you have antiviruses blocking the malware. So if you can take the malware that is attacking the specific organization, it's all sitting in the quarantine. No one wants to analyze that malware, just sitting there. And we could do some kind of analysis here, add some external threat intelligence, and maybe develop an attacker profile. So you got hits coming in, you get a sense of who is the attacker. Maybe you can get something about threat actor, who are they targeting, what do they want to do, and create local threat intelligence. Local as in for you, your organization, not someone else's organization. It's your bank, some other bank. It's your manufacturing environment rather than some other manufacturing environment. So if you can construct that, of course, that will be valuable. So that's the philosophy track. So I'm going to switch back to operational track, because I believe I have some little piece to the answer to this puzzle, small piece there, but not. So current state of malware analysis broadly is in two areas. You can say reputation, places like VirusTotal, you take a hash, you throw the hash, it tells you something, you say, it's good or bad, you get a reputation. A lot of services that do reputation, they've already studied the malware, so they are binary, they already know. So they say, okay, tell me about it, you get it, it's done, reputation. Of course, if you don't know anything about it, then you throw it in a sandbox. There's a whole bunch of sandboxes you throw in a sandbox. You get a lot of information, you dig through it, you figure out, okay, this is good, this is bad, and of course there's some more automated analysis you do. And so you have this space in between. If you find something, good. If you don't find something, you analyze and so on. Now, what we have introduced through my research and now into practice is a content-based search for malware. So content-based search comes from information retrieval, where like Google Images is content-based search. You can upload an image on Google and it'll tell you other similar images. So you're not doing Google sort of query, you just put the whole image and say, okay, tell me what it's similar to. So in the same spirit, we have a content-based search. We got a malware collection, new malware comes in and say, oh, this is what it's similar to. So it's just search. And of course, once we have a content-based search, in this case, we are using code content-based search on code, you could potentially do similar thing like there was a talk yesterday about behavior. So you could have a behavior collection, you throw the malware in, maybe you'll extract the behavior, do some analysis and say, oh, these are all the similar ones. So, but we do content. And then, of course, since we are doing it based on code similarity, we are finding similar code, we also use the similar code to create Yara rules. So that's the process. So we talk about use a malware to catch a malware. Essentially what it means is if I know I have a malware, I can throw it in a collection, get Yara rules, get a lot more information, and now I can use the Yara rules to go about catching the malware. So here's the example. If I upload the malware, I get similarity malwares. These are the malware that are similar. We do unpacking, a little bit of unpacking where it works. So we can say, hey, this is the packed version. So these are all the packed versions, similarity with the packed version, similarity with the payload, sometimes payload matches, sometimes it doesn't match. So here it says similar packer, different payload. So we do some level of similarities. It's all based on code, except for the unpacking part. So once we have the similarity done there, then we have the key question is, okay, how do you deal with polymorphism? So that's the part in malware is obfuscated. That's where all your hashes and change. And so how do you deal with polymorphism? So this is an example of polymorphism where if you have a little piece of code, the packer so program could transform it. All of it is doing the same stuff. They all look different and all. Okay, this is a more complex version of it. Most of the time, what I've seen in in real code, I've not found this level of complexity. But this is a more so. This becomes the major challenge in code content-based search. So what we do is essentially take this stuff and run it backwards, so to say. So we do symbolic interpretation. So symbolic interpretation really means that you execute the program, but you execute program symbolically. Symbolically means you sort of compute what is it going to be doing. So you don't have actual variables, you don't have actual registers, you say symbolic register. So you compute a symbolic expression. It's like linear algebra. It's like simplifying linear algebra equations in linear algebra. So if you take each of the expression, you can compute a big linear algebraic expression about what it's doing, and then if you simplify it just like what you do in linear algebra, you simplify it, you get the simplest answer, and say, okay, this is my answer. So that's a simplification, so it's symbolic interpretation. So that becomes the key. And you have, FireEye has something called Symbolics. They have an open source project called Symbolics. It does the same thing. You throw code in, and it could simplify things for you. There are other environments like this is all done in the compiler context. A lot of people in compiling, they do that where you have you give it a little piece of code, it's going to transform it to some internal form, do some simplification, gives you back some code. Now what we do is take this as the basis of taking the code and simplifying it, and from there on we have a slide. We use this to sort of create the biggest jargon today, machine learning. So we take this, use the semantics to construct features so that we can find similar functions. And once we can find similar functions, then we find similar binaries and say, okay, these are all similar binaries. And so next what you can then do is construct Yara rules. So this is the Yara rule here. If you would see, I don't know if it's visible there, but this is the byte string. This is a hex byte string at the bottom. And you'll have some question marks, as in where we find some polymorphic changes, put some regular expression. It's all automated. So you have similar code. You look at the similar code. We know this code is similar because the semantics is very similar. And I'm using the word similar here rather than equal. And similar, we have a little bit of fuzziness that we can allow where they don't have to do exactly the same thing. It could have slight differences. And there we match, create regular expressions. So now you have Yara rules. And how do I construct Yara rules? Again, go back to some of the basic computer science thing you get taught in regular automata theory and stuff. We take control flow graph. Program is control flow graph. We already found matching procedures, so we know they match. They're the same. And once you have found matching procedures, we take the control flow graphs and convert it into automata. So it's almost classic done stuff. Take the graph, map it into automata in some sort of transition, and then you take automatas from two functions. They're similar. So as you take a union of the automata and say, okay, now optimize it. So sort of reduce the automata. So wherever you need to find things that are asterisks, could we go there? We put it there. So sort of minimize automata. So it's a reasonably old trick known in automata theory. We use that, and we got rules there. So this is an example of procedures. So here you see procedures. So we look at all of the procedures. We find procedures that are similar. We look at a lot of properties. So the big part is once you find similar procedure, you still have to say, hey, is this malicious? Most malware nowadays, they may have libraries statically linked. And so you got library code. And if you match library code, you're going to be freaking out on some Windows DLL or whatnot. Okay? So you don't want to necessarily create false positives. So what we do is we have each of these rows here represents a function in the malware. And we compute a whole bunch of properties of the functions. Of one of them is it a library? And the way we associate library is a transitive property. It's a strong property. If A is similar to B and A is somehow library, then B is library. So we just say it's a strong property. If anything matches a library, it's a library. So we throw in DLLs. We take IDA flirt and say IDA flirt says this is library. Okay, IDA is king, library. So we go exhaustive. Even if it's not library, you don't mind. If anything says this is library, this is library. Library. So that's one way. The other is we also have, it's not in the screen, but we also have occurrences. We count like, okay, we have a large collection of malware. We have this function. How many times does it occur? So it's extremely large. We say, well, it's most likely library. It's too spurious. You can't have one function in like 10,000 or 100,000 different malware. Maybe it can, but we'll treat it as so we have about 8 million in our collection right now of malware. So sometimes we find 20, 25 million matches because there are multiple copies of the same function in the same binary and so on. So we use some more information here to determine what is the likelihood that this is a malicious program code. And with that, then we go select, okay, I think this is a, we also have a notion of variants. We say, hey, is this a variant? So we find it doesn't have to match exactly. It could be polymorphic variant. So it may have more blocks, more instruction, less instruction. We find variants. We classify them and say, okay, let's look at what we can use to construct the rules. And then we go about constructing the rules. So this is an example. I would be happy to show a demo. If we have some time, I can connect and demo as well. But it's based on solid code. So I can show you, like, it's just incredibly nice to look at code that is similar with small variations and all. And we construct signatures there. Okay. So in the spirit of we started one of the early I think Jason said, tell about what you can do. What do I do? So that is what I do. Then what can I offer? I have this service available, Magic service. You upload malware. It gives you analysis and all of that stuff. You're available to use. I can offer that free for you to drive it hard. Okay, it's pretty good. I think it's very solid, but it's still, of course, rough edges there. And the key part in this service I found from experience is not so much of the algorithm, but the data. It's like 7-8 million malware processing takes forever. I mean, it's taken me a long time to get there. So the analysis, the depth of analysis, yep, it can be replicated, but the data is the hard part, I think, analysis to create a large collection. And the large collection is really what the big part we offer there. And what I need, now this is a vision. I started early, hey, these antiviruses are not essentially being used enough, I believe. That's where I'm starting from. Say, you quarantine malware, you stuck it there, you forgot it, and nothing is happening with it. Well, nothing is happening with it because it's too much work to analyze it. So what I think we can do is analyze it automatically. So what I'm looking for is the places to pilot where we connect with the antivirus, pull the malware, pass it through Magic, construct Yara rules, and pass it to things like IDS. Bro IDS, for example, takes Yara, or pass it into SIM or EDR devices and so on to automatically plug Yara rules that are created based on the threats that reach your network rather than just the threats that are happening somewhere else. Okay. That questions? Okay. I'll need a little question translator. I'm going to come near because I have a hearing problem. Let's come closer there. Yeah.
So I'm not familiar with Drill until now. Is that an open source project or what?
No. So there's not, the whole thing is not open source. There's a core component of it which does analysis to extract the semantics. That is open. But there's a whole bunch of things built around that's not open. Okay. Yeah. Okay. Walk through there. All right. Sorry. Yes, Can you repeat it? Go again.
Are you using the disassembly to compute the features or rely on another pro?
Yeah. The question is, are we using disassembly to construct the features? Yes. So we do use disassembly. So there are limitations. First is we do disassemble. We do unpack to some extent to where we can. So we run it in a VM, wait for some time, flip a little bit of coins, and then say, okay, it's done, and we pick up some. So 60-70% of the time it seems to work. Other times it doesn't work, but we do some. But once we unpack, we again disassemble that too. So we disassemble the original, disassemble the final, and from there then we go about computing all of the stuff. Yeah. Okay. Yeah. Yeah. Huh?
How did you build your original training corpus?
So that's a good question here. How do we build a training corpus? Now that is a big challenge in malware, the business of training. The training, as in the classic thing about training, is you have a sample, you associate some known property to it. Okay, this is good, this is bad, this is family A, family B, and so on. And the training is important if you build a classifier. A classifier is that you get a new malware, throw it, it puts in a class. It's a big challenge in malware space because how do I build good training data? So what we decided is we're not going to worry about training. Instead, we are doing search. In search, what we do is we throw a whole bunch of collections. So we have a large collection of malware. And we're not per se training, we're just searching. So we are searching for similar malware. So once I find similar malware, like in this case, I had this some 10 or 15, sometimes 1,000 similar malware. Then we say, okay, these are similar. I know these are similar. Let's look at the reputation. So now I go back to reputation. Let's look at the reputation of these other 10, 100,000 or so similar. So I'm not per se saying these are bad. I'm not saying it's malware. I'm saying, hey, I can search and tell you whether they are similar to anything known. I can search based on similar code. And when I say things are similar, I have a high degree of confidence that this is really similar. It's not fake. I can actually show you the similar code. I can point and say, okay, this is where the code is similar. So I do similar code. Is it good? Is it bad? That's not nothing I'm saying. It's whether good or bad. There we go, reputation. And assuming it is bad, then I say, hey, I can construct rules based on code that is similar, and then based on some heuristic I use to say this is most likely a good representative of the malicious code. So any code will have good and bad code in there. We don't want to randomly pick any code and say, okay, I'll use this. So I'm not making a claim of antivirus. I'm not being an antivirus. I'm do code search, find things that are similar, construct a rule, and then use other indicators to determine whether it's good, bad, or somewhere in between. Okay.
Any other questions in the room? You said if you had time, you could show us a demo.
Sure.
Let's see a demo.
See?
Let's see it work.
Yep, I'm going to connect just there. Give me a little moment, and I connect to the internet. So typically you have your standard stuff of uploading some malware. It goes through some processing, so not immediate. So you sometimes want to check, okay, where does the processing stand? So we have some monitoring the status, and then this is something called a report search. And we also have, if I have a large collection of malware, put it in some context and give a little bit more information rather than individual malware. So we have something called this early warning system. And this is a little thing we have created where we keep throwing malware in every now and then and create some database. So this is showing that this is the timeline. Each little dot here represents a malware here. Each little dot, say, is a particular SHA. And then we also have this thing called clusters. The size of the, this is a collection of size 7, which are similar. And this is a little larger one, size 141, similar. The similarity based on code. And then what you do is you want to search similar code, and I have some samples sitting there. So I do similar code. So it's going to go through and show. Let me see if you need a bigger. It's too big. This is so it says it matched 43 entries, and here this is based on. This is we get malware feed from few sources, so we get about 15,000 or so malware data every day. So we stick it in there. So this is based on some similarity with our collection that we get. So, and then we have a notion of payload similarity. Let's see. In this one, we don't have much of a similarity at the payload level. So when I say packed similarity, I'm assuming this is packed. If I can't unpack it, I just still call it packed. So it could be a file that is really not packed, or we couldn't unpack it. So we are just saying whatever is the original, this is where it matches. So this is a 0.8913. You can go do something like a bin diff. This one I have an error loading data. This is that one. Let's see. Okay. So here is the, it's like a bin diff of sort, but so this is showing that file 1, file 2, location RBA, the function, this function matches the function of line 29. Here I'm showing what I call as clones, and so this matches. So this is a match of the function. And you see the RBA are different. So what I found is most of them, they don't have a lot of great polymorphism. All they have is a code shuffle. Code shuffle is relatively easy to catch. There's nothing much in there. But so this is a similar code. And so you can find, let's see, if I sort it on size, you have pretty large functions that are exactly the same. So it's a huge amount of functions that are same. In this case, 42 of the functions out of 44 in the total collections are same. So it's like not a whole lot of that is different in there. So that's where we do the similarity part. And then you can go and say, all right, make Yara. And then it will construct the Yara rule. So this is our own internal indicator for a function. What function am I using? Yeah. Just a second, let me come there. Yeah.
When you print out the components for the strings portion, are they ordered?
Ordered as in no,
And where you would see them within the binary?
not necessarily. No. So the question is, are the strings ordered in where you would see them in the binary? That works when you are looking at one binary, but if you look at the function similarity I showed you just now, what you find is that these orders, the address here, they don't always match. Things get shuffled around. So if you take a function and say this function should occur first, then the next one, then the next, it's too rigid. It will work, but it'll be too rigid because all they're doing is shuffling functions. Okay, so as we go forward, we could probably look at more stronger indicators, but really we just want to say, hey, what I think the key part is, how do I know is this bad? I mean, what if it's just some picked up happened to match some let's say DLL code? Okay, it could accidentally match, not just happen to match. I mean, I just wrote the same code. Turns out similar code is available elsewhere. So that I think is a bigger issue and so for that, what we do is, so here's the case. Let's see if I look at procedures. So this each row is some information about the procedure here, each row. And if I look at the name list here, that's the important one. I'm going to sort it. Just a second, name. So remember we do association. So if I have a function that's similar to another function and I have a name for that one, I say, okay, let's pick up that name. Okay. So here what we are finding is in my collection there's 830 copies of that function. Right? And for now we're only picking the top 10 names. We don't pick all of the names. So just why it says only 10. And those 10 were all named libc weight. Okay. It's libc weight. Although IDA flirt did not mark it as library for me. None of them was marked library, so it's not library. So right now IDA flirt is my king, or DLL, I couldn't match it. So maybe I didn't have enough DLL, right? So I got a name here. So that's one important thing. You associate, get the names of functions. So you have similarly here, now this is a huge collection, 648. And let's see. Sleep, end, thread, file, close. These are the various names for similar code. So we have, this is not always exact name, but so if I was using, let's say, this function as a signature, I might end up creating a wrong match. Okay, the functions. So what we do is first is to say, let's see some more here. This is these are somehow the code is similar. They seem to be doing different work, but the code is similar in my definition of similar. Okay, so we don't want to use this code. So we use some notion of occurrence. It should not occur very high, and we're still working on tuning that part. The occurrence, if it's very high, very low, so it's like Goldilocks sort of thing. We want to just right. Okay, not too high, not too low. Just so we're trying to find that right balance, and then we use this to select the rules. And so here's the rule selection. So, and then this is a small code. So we say, well, it should not be too tiny code. 10, 15, 20 instructions are easy to match. So let's try to a little big. And we don't want to have too big because that might be too rigid. It just matches one instance. Who knows? Or the search will be too expensive. I don't need a huge 50,000 line byte function. It's something right. So we are trying to strike a balance. And that's still an experimental stage here. And so here's the example of true. This is these are all marked as library here. And if you look at the name of the function, sometimes they will match. There's some concurrent queue wraps on. So it's all automated. The key is, okay, typically you would do it as a human analyst trying to match code and find this is similar, this is bad, and this is where it's malicious, so to say, and use that malicious as a TTP for going further to have any kind of indicators. Here we do that pretty much all automatically.
All right, Arun. You're going to need to wrap it up, but
Yep.
thank you very much.
Okay.
Much appreciated.
Thank you. Thanks.